When you look at your statistical output, you're going to realize that it's pretty involved. There are a lot of numbers, so I'm going to use this video to help you make sense of what you're looking at. I'm also going to simplify your life by letting you know that the majority of these numbers you don't even need to pay attention to for the purpose of this manuscript. If this were a real study and a manuscript that you were planning on publishing, then all of this data would be relevant and important. But I'm going to try and simplify some things and narrow down the types of comparisons and number of comparisons that we're going to be making in this study. So the first thing that you see is that we have data listed up here for the subject characteristics and for the actual experiment that we conducted. The subject characteristic data you don't really need to worry about for a couple of reasons, and I'll go over those in a moment. So what you're really going to emphasize on this page is this information here, and that's the time trial, where we're going to want to know the time trial time, the mean power, and the respiratory exchange ratio at each of the different distance points throughout the time trial. This is broken up into two different sections. One section is looking at between groups, and another section of the statistical output is looking at information or the difference within experimental groups. At the end of your method section, you were to copy and paste a paragraph that I wrote for you with your statistical methods. It is not It's not an objective in this course for you to understand really what those statistical methods are, and that's why I wrote the paragraph for you. But indulge me, since I didn't have you write your own paragraph, indulge me for a moment and let me explain to you a little bit about what those tests are and why they're being used. You have three different groups. You have fat loading, carb loading, and a control group. And they were exposed to the intervention, which is what their groups are, the fat loading or the carbohydrate loading or control, and then they all went through a time trial performance. And so what we're going to see is that we have between group comparisons that are being made as well as within group comparisons that are being made. In order to compare the three groups, the first question that we want to ask is there a significant difference between the three groups? And that's why we use this analysis of variance, ANOVA, because it tests for a difference between the groups. The question that is being asked, is the ANOVA significant? In the other tutorial video that you've already watched, you found out what a p-value was. And I told you that when you have a p-value that is less than 0.05, that indicates that there is a good likelihood or a high probability that the difference in the comparison that's being made is a result of the treatment and not due to chance. And so now we have a whole list of p-values here. The initial question, remember, that we're asking, is there a difference between the three groups? Now, if there is a significant difference, we don't know what the difference is, but we know that one of the three groups is significantly different from the other two. So when we look at these p-values, using subject characteristic data as an example, all of these p-values are greater than 0.05. That lets us know that there is not a statistical difference between any of the three groups with respect to their baseline age, weight, VO2 max, or peak power output. Now, we would not expect there to be a difference in these baseline subject characteristics because they were randomized into the three groups. And we want all three groups to start out at the same point. So that makes a lot of sense that there is not a statistically significant difference between the three groups at baseline. But then with respect to the intervention, we have some values that are significant and others that are not. These first two, the 100-kilometer time trial performance, is not significant because this value here is greater than 0.05, as is the mean power throughout the time trial. So what that tells you already, without any further analysis, is that fat loading, carbohydrate loading, and control are not different from one another with respect to their time trial performance, how long it took them to complete the 100 kilometers, and their mean power, their average power output during that 100 kilometer performance. What was different, though, was their respiratory exchange ratio, and that is also something that you would expect to be different. It's unfortunate that the difference in diet didn't result in a difference in performance, as in how quickly they could complete the 100 kilometers, but you would expect that if somebody is eating a different diet, that it would alter substrate utilization during an exercise bout, and that did in fact happen. So what we know from the ANOVA is that one of the three groups is different from the others with respect to their RER at rest and at 25 kilometers, 50 kilometers, 75, and 100 kilometers. But what we don't know from the initial ANOVA is which group is different from which other group. And so the next thing that we do is, for significant results from the ANOVA, we then perform pairwise comparisons to determine which group is different from the others. If the value is not significant, we just stop there and don't go any further. So we will not be doing any further analysis on 100 kilometer time or mean power. We are just going to indicate that there is not a group difference for those values. So we will ignore all of this information on pairwise comparisons because the initial ANOVA was not significant. Now for RER, all of these values were significant, so we are in fact going to continue on to perform pairwise comparisons. But here's where I'm going to make your life easy. At rest, we would want to know, is the control different from fat, control different from carbohydrate, and is carbohydrate different from fat? And we would have to repeat that process at each of these distances. And we're not going to do that. Let's all agree that when you go from rest to exercise, the RER is going to change. You're going to go from more fat utilization to more carbohydrate utilization, and your RER is going to climb when you go from rest to any level of exercise. So we're not really going to concern ourselves with the resting values. Instead, what we're going to do is we're going to concern ourselves with 25 kilometers, which is our first distance of exercise where we measured RER, and then the final RER value at the completion of the 100 kilometer time trial performance. At rest, or I'm sorry, at the 25 kilometer distance, when we compare control to fat loading, we see that there is a significant difference. Now this is not directional. It doesn't give you the means and standard deviations. You'll need to look at the means and standard deviations to figure out which one was greater, but we just know that the control is significantly different from fat loading. In fact, all three groups are different from each other. The control is different from fat, the control is different from carbohydrate, and fat is different from carbohydrate at the 25 kilometer distance. You're going to skip the 50 kilometer distance, the 75 kilometer distance, and go straight to the 100 kilometer distance. At the 100 kilometer distance, we see the exact same thing. All three groups are different from each other, indicated by p-values that are much, much less than 0.05. So for the between group comparisons, we're only looking, once again, at the 25 kilometer distance, and we're looking at the 100 kilometer distance. Now be sure to note that although I am not asking you to evaluate significance at these intermediate time points or distance points of 50 kilometers, 75 kilometers, and rest, they do still need to be included on your graph, on your line graph. So your line graph will still have rest, 25 kilometers, 50 kilometers, 75 kilometers, and 100 kilometers, but you'll only be worrying about indicating statistical significance on your figures at the 25 kilometer time point or distance point and the 100 kilometer distance. Now, in addition to looking at the between group comparisons, we also want to know, did RER change from rest to exercise to 100 kilometers, and that would be within group comparisons. The initial ANOVA is just asking the question, is there a difference somewhere in there within the group when considering the RER values at rest, 25 kilometers, 50, 75, and 100 kilometers. Now, for each of these groups, all of these values are significant, and that tells us that we do need to look at all pairwise comparisons. But I'm going to really simplify your life once again, because what I'm really interested in is not any of these values. I just want to know from the first exercise measurement, which was at 25 kilometers for RER, is the RER at 25 kilometers different from the RER at 100 kilometers? For the control group, all of this is control. For the fat loading group, and for the carbohydrate loading group. For the control group, when you look at this p-value is much greater than 0.05, and so this is not a significant difference, meaning that while there's probably a numerical difference between the RER for the control group at 25 kilometers and at 100 kilometers, it is not statistically significant. Likewise, for the fat loading group, there is not a significant difference in RER from the 25 kilometer distance and the 100 kilometer distance. But for the carbohydrate loading group, there is a significant difference from the 25 kilometer distance and 100 kilometer distance with respect to RER, indicated by a p-value much less than 0.05. So to summarize what you'll be doing, when you have your figures, you'll have three figures. One figure will be for your 100 kilometer time. One figure will be for your mean power, and these two figures will both be column graphs. And then you'll have a third figure, which is your line graph showing RER at all distances, at rest, 25, 50, 75, and 100 kilometers. Because there is no statistical difference between groups with respect to 100 kilometer time and with respect to mean power, you will not have any symbols of statistical significance on those two figures. However, for your line graph, you will need to utilize multiple symbols to indicate significant relationships. And those significant relationships I've already highlighted for you so that you don't have to locate them. So I've really tried to simplify your life, but I do want you to have at least a basic, fundamental understanding of what a statistical analysis is, how to interpret it, and what it means, so that when you're reading a paper and you see p-values, you kind of have a little bit of an idea of what they mean. Importantly, when you write your results section, it's really important to present your results in terms of direction and in terms of significance. So it's not enough to simply state that one group is different from another group. You need to indicate that it's directional. One group was greater than another group, and you also need to indicate whether or not it was significant or not. So a proper way to present a result would be to say that one group was significantly greater compared with another group. That way it's both directional and you indicate whether it was significant.